Today we are reviewing multiple choice topic 3, which is on integration. So if it was hard for me to review all the different types of differentiation, derivatives that we can do, it's going to be simply impossible for me to adequately review all of what we've done with integration in a short period of time. But we can hit on some highlights. So first of all, for the definite integral, this is a Riemann sum definition of an integral, a definite integral. Know that. These will appear in multiple choice questions. Also, know approximations for a definite integral with all the Riemann sums, trapezoidal sum, midpoint sum, things like that. For integration, we relied on the power rule a great deal. So the power rule is huge. And then we had a lot of different techniques for integrals. We could apply U substitution. We did that a lot. Dividing an improper rational function that's in the integrand. Remember, if the degree of the top is greater than or equal to the degree of the bottom, you go off to the side and divide. Partial fraction decomposition to integrate. Completing the square in the denominator to integrate. Integration by parts. Improper integrals, where perhaps one of our boundaries is infinity or one of the boundaries is the location of a vertical asymptote. We always remember to write these as limits. We also covered trig substitution and integrating powers of trig functions. Those techniques are not tested on the AP exam. So very brief overview of the different techniques. Also know all of the special cases, all of the integrals of trig functions. You need to know those. Integration of 1 divided by a linear function of x. We go to this and we use sub if we need to. Integration of exponential functions. Integral of e to the x is just e to the x. Integral of some other constant to the x, you have to divide by the natural log of that base. It's the opposite of what we do for derivatives for those kinds of exponential functions. Integration of natural log x. This is one that's very nice to memorize. If you don't memorize it, then you're going to need to go do by parts integration to get that answer. Also know the form of the integrals that will give you an inverse trig function. Know those forms. One word of thought here. Back on our formula sheet, I printed this off for you in yellow. This is the back of the first page. All of the derivatives that you should know, all of the integrals you should know. So that's pretty important. Okay, let's just look at some examples. Again, I can't possibly give you an example of everything, but I can give you a few examples. Number 1, when we have a problem like this, I need an e up on top, so I'm going to multiply top and bottom by e to the x. We've had several of these. Hopefully these are not a problem for you anymore. On top we'll have e to the x. On the bottom we'll have e to the x plus e to the x times e to the negative x is 1. Now we can go off to the side and do a u sub. U is our denominator. So du here is e to the x dx. There's my du. Here's my u. So this is just 1 over u du, which is the natural log of the absolute value of u, where u is e to the x plus 1. Number 2, this is in the form of arctan. It's in that form. So this is kind of a basic one, but if you want to, you can come off to the side. Our u will just be an x, so du is just dx, nothing more than just a du there. A will be the square root of 8. So for arctan, we need 1 over a. Arctan u over a plus c. So don't forget those. Number 3. This is just a u sub. I'm going to let u be the bottom because du will have an x in it. So u is x squared plus 2. Du is 2x dx. So 1/2 du is x dx. So in place of x dx, I'm putting 1/2 du. So we'll have 1/2 integral 1 over u du, which is 1/2 natural log absolute value of u, where u is x squared plus 2 plus c. As a multiple choice answer for both of these answers, 1 and 3, they would not have absolute values there. They would have parentheses because that argument can never be negative. But we don't need to worry about that. Okay, number 4. Well, for this one, I see that exponent, and if I let u be that exponent, whenever we have a complicated exponent, let u be that exponent. Du here is 6x dx. I have the x dx, so I just need to move that 6 over. So in place of this x dx, I'm putting my 1/6 du, and that exponent now is just a u. So we have 1/6 integral 5 to the u du, which is 1/6. I need 1 over ln of 5, and then it's just 5 to the u plus c. Number 5. Well, here I cannot let u just be the 3x because du would just be a number, and I have x squared out in front. This is one where we can use by parts integration because I have an algebraic function times a transcendental function. This is a good one to do using a table. So I'm going to set up my table, u and dv. My first u is x squared, and I know and then my first dv will be everything else. I take the derivative of my u column until I get to 0. I take the integral of my dv column until I line up with the 0. So the integral of cosine of 3x is 1/3 sine of 3x. Take the integral again. Well, the integral of 1/3 sine of 3x will be a negative 1/9 cosine of 3x. Integral of negative cosine is negative sine, so negative 127 sine of 3x. Don't forget, we are multiplying these diagonally, and we start with a plus here, positive of the x squared, negative of the 2x, positive of the 2, and we keep alternating that sign as we go down. So we'll have a positive x squared times this 1/3, so that will be a 1/3 x squared sine of 3x. Now here I have a negative 2x and a negative 1/9, so that will be a positive 2/9 x cosine of 3x, and then this will be a negative 2 over 27 sine of 3x plus our constant of integration. A little by parts table method. Number 6, integral of secant squared x is just tangent x plus c, because the derivative of tangent is secant squared. Okay. Number 7. For this one, I noticed that the denominator, well, can the denominator be factored? Can the denominator be factored? It can be factored because it factors into x minus 6, x plus 2. If we can factor, I'm going to go off to the side and do partial fraction decomposition. Little partial fraction decomp, and then we'll integrate. So I'm going to multiply both sides by the common denominator here. And now I can let x be anything I like. I'm going to start with -2 to make that a term 0 out. I'm going to have -6 is equal to -8b, which means b will be -6/8 or +3/4. If I let x be 6, I'm going to have 18 is equal to 8a. So a is 9/4. So in my integral becomes the integral of 9/4 over x minus 6 plus 3/4 over x plus 2 dx. And from here, it's very easy to integrate two little natural logs. And we're done. Little partial fraction. Okay, number 8 here, the integral of secant x. Well, I don't know a trig function whose derivative is secant x. So these are one of the other ones that we memorized. This is going to be the natural log, the absolute value of secant x plus tangent x plus c. Memorize that. That's on our list of things to memorize. Number 9, can we factor this denominator? Well, I look at it and I cannot factor it. If I cannot factor it, I'm not going to do partial fraction decomposition. Instead, I'm going to try to complete the square in the denominator. These were not bad. Completing these little squares are not bad. In fact, I'd rather complete the square than to do partial fraction decomposition. I take half of that -6 and square it, and then I add to this 9 whatever it takes to get to 20. And now I'm going to factor just this first three terms in the denominator. That's going to be an x minus 3 squared. And now we just have an arctan. So this will be 2 over the square root of 11, because a is the square root of 11 here, arctan u over a plus c. Not bad at all. Way quicker than doing a partial fraction decomposition. Number 10. First thing I notice is I have an x cubed polynomial on top, an x squared polynomial on the bottom, so I need to go off to the side and I need to divide. I cannot use synthetic division because of this x squared, so I need to use long division. So x squared times x is x cubed. Now I'm multiplying x times x squared minus 1, so that'll be x cubed minus x. I subtract this minus this. So the x cubes are gone. Negative 2x minus a negative x will be a negative x plus 1. My degree is now less than this x squared, so I'm done dividing. I come back to my integral. This will be the integral of x plus my remainder divided by my divisor. I know how to take the integral of x. Over here, though, what do we do with that? Well, I see this negative x minus 1. I want to factor out a negative because I know I can factor x squared minus 1. It's a difference of squares. So I'm going to factor out a negative 1. This will be a positive x minus 1 on top now. And in the bottom, I have x plus 1, x minus 1. The x minus 1's cancel out. And now I just have my little natural log x plus 1 left. Power rule on the integral of x. Number 11. Again, I see I have a power of 3 on top, a power of 1 on the bottom, so I know I need to go off to the side and divide. This time I can use synthetic, so I'm very comfortable with synthetic division, so I like to use it whenever I can. I put in the opposite of this positive 2 in the box, and then I need the coefficient for the x cubed, a coefficient for x squared, the coefficient of the x, and my constant. bring down your first number, multiply, add, multiply, add, multiply, add. So my integral becomes the integral of, this was an x cubed, so this will be an x squared because we're dividing out an x. So x squared minus 2x plus 2, this is my remainder, so plus negative 3 divided by my divisor. The rest of it is just power rule and a little natural log. So 1/3 x cubed minus x squared plus 2x minus 3 natural log absolute value x plus 2 plus c. Okay, number 12. We've got one of these types of questions where they're asking us, do we know that Riemann sum definition of a definite integral? So what I look for first, I see a 2 here, so I know I'm going to need a 2 in front of each of my little sets of parentheses. So I see the 2 here, I see the 2 here, I don't see it here, I don't see it there. So I've narrowed it down to these 2. So the next thing I look at is I need for my b minus a to be 3. So I'm looking for a 3 here, a 3i here, but I also have a 3i there. So how do these two differ? Well, this has what appears to be an x term with the 7. There is no x with the 7, so I know my answer is B. Those are some of the things I look for with that. So how else can they ask us if we know how to integrate? All of these problems that we've done so far, 1 through 11, for 1 through 11, there are calculators that can do that. So how can they find out if we can integrate if we have a calculator in our hands? Particularly if you're taking an online exam. This is how they might ask you, if you know how to integrate. So, because a calculator cannot be used on these. So let's see how we would do this. We have a table with f prime in it, and then I have this integral of f double prime. Well, the integral of f double prime is f prime. We always go down a degree, a derivative degree. So this would be f prime of x evaluated from 2 to 3. So this will be f prime of 3 minus f prime of 2. Another way to do that is to skip straight to that because this is the fundamental theorem of calculus. F prime of 3 we get from our table. F prime of 2 we get from our table. So we get 4 and we're done. Over here. Well, first thing I notice is that we don't just have an x here. This one we just had an x, so we didn't have to do anything to it. But here I don't just have an x, so I need to come off to the side and do a u sub. Du will be 2x dx, so 1/2 du is x dx. I have the x dx out here, so I'm substituting in place of that 1/2 du. Here's my u, so this becomes the integral of, well, I need the 1/2 out in front, 1/2 the integral of f double prime of u du. Now my boundaries I need to fix because I changed it to u's. If I put 2 in for x, I get 7 for my new upper boundary. If I put 1 in for x, I get 4 for my new lower boundary. So this will be 1/2 f prime of 7 minus f prime of 4. 1/2 f prime of 7 from the table is 11, f prime of 4 is 8, so 3 over 2. Number 14, this is another way that they could ask us, do we know how to integrate? By a table, by a graph. We just did a table. By a graph. So this is the graph of f, and they're asking me something, well, first of all, I see this. This looks rather awful, but if you keep things straight, this exponent is not just an x. So I know I'm going to need to go off to the side and do a little u sub. U is f of x because that's your exponent. So du is just f prime of x dx, which we have sitting out here like a little Christmas present for us. So in place of f prime of x dx, I'm putting my du. Now I just have e to the u du. Integral e to the u du. I need to mess with my boundaries. If I put in 5 for x, I have f of 5. Well, what is f of 5? This is the graph of f. F of 5 is -1. So my new upper boundary is -1. I put in -4 for x. F of -4 is 1. So I have this integral to solve. My boundaries are off, so I'm going to change it, put my smaller boundary on the bottom, my larger boundary on top. We don't have to do that here, but you can. So now we have e to the u, the antiderivative of e to the u is e to the u, from -1 to 1. So that is negative e to the 1 minus e to the -1, which is negative e plus 1 over e, or 1 over e minus e. B. Well, the first thing I see is that I don't just have an x here. So go off to the side, do a u sub. Du is 4 dx, so 1/4 du is dx. So in place of dx, I'm putting 1/4 du. This is now u. So my integral becomes the integral of f double prime of u du. Oh, I forgot my 1/4 out here again. Let me go slide it out here. Not negative, just 1/4. Okay. My boundaries. So my new upper boundary, 2. If I put 2 in for x, I get 8 minus 5, which is 3. If I put a 4th in for x, I get 1 minus 5, which is -4. So this becomes 1/4 f prime of my top boundary minus f prime of my lower boundary. So we have the graph of f. How do we get f prime at 3? Well, that's the slope of f at 3. And at 3, the slope is a -1. At -4, the slope is a 0. So this is just -1/4. Part C. Well, I don't need to go do this type of u sub, but I have this x out front. Well, if we have the x out front, and I can't do a plain old u sub, this is a by parts one. So I'm going to let u be x from this x. I'm going to let dv be everything else. So du is dx, and we integrate to get v. The integral of f prime is f. And remember, u times v minus the integral of v du. uv minus the integral of v du. Okay, and now I'm applying my boundaries. So I need to take this from -4 to 2. This integral still has -4 to 2 on it. So this will be 2f of 2 minus -4 f of -4 minus, okay, the integral of f of x from -4 to 2, I can go use areas. So from -4 to 2, -4 to 2, I need that area. So this piece will be 1/4 pi r squared, 1/4 pi times 1. So 1/4 pi. This is going to be a -1/2 pi r squared, where r is 2. So -1/2 pi r squared, where r is 2. And then from 1 to 2, little triangle, positive because it's above the x-axis, 1/2, 1 times 2. Okay, f of 2. f of 2 is 2. f of negative 4. f of negative 4 is 1. And then, since I have to rewrite this anyway, I'm going to distribute this negative through. And we could clean that up for a multiple choice answer. Let's see, 8 minus 1 is 7, plus 7 pi over 4. They might leave it like that. They might get a common denominator. I doubt it. I bet you they would just leave it like that. But either way is fine. Okay, part D. Very similar problem, because we can't do a plain old U sub. We need to go off to the side and do it by parts. So U is x, dv is everything else. du is dx, v is f prime of x. We do uv minus the integral v du. uv would be x f prime of x minus the integral of v du. And now go put your boundaries back in. We need -1 to 3, -1 to 3. So this will be 3 f prime of 3 minus a -1 f prime of -1 minus, okay, the integral of f prime is back to f. So f of 3 minus f of -1. Okay. F prime of 3 is the slope of f at 3. That's -1. F prime of -1 is the slope of f at x equals -1. Well, at x equals -1, the slope is 0. F of 3 is 1. F of -1 is -2. So we have a -3 minus 3, which is -6. So, integration. We did so much with integration. It would be impossible for me to show you everything. So, anyway, go practice some and see how you do.